Okay, having now understood a little bit about how material elements flow through a system, how they might translate, be rotated and deformed, and we've thought a little bit about the different kinds of deformation, if we're going to write down a conservation equation which says something is conserved, maybe mass is conserved, or momentum is conserved, or energy is conserved, then we're going to have to think about what those kinds of forces are that are going to be acting on a system as it's flowing, and so that we can write down a conservation equation for any of these variables. And the most important one that we're going to be interested in ultimately is in conservation of linear momentum, and linear momentum is proportional to the mass, of course, and the velocity, and we're going to write it down on a per unit mass basis, in which case we're really interested in this velocity vector v. So to do that, we're going to have to think about what forces are acting on a system, and we want to do this for a general kind of control volume or material element that I've kind of indicated schematically here. So this is a completely arbitrary system with a little element inside it that we might call dv, and this overall system, if we integrate it over the whole region, is what we might call a material volume. And the material volume may be moving and flowing, so we need to write down the idea that it could have a velocity v everywhere, which is a function of position in time. So we're going to be thinking about an Eulerian coordinate system. And then an important part of what we're going to be interested in is the idea that we're going to have to frequently integrate around things. And so we're going to be interested in thinking about a normal pointing outwards. So we'll always use the base vector n to indicate a normal vector, and that's going to be pointing outwards. And it's worth recognizing that when we think about it this way, area is really a vector quantity. Area is a vector quantity because it has a magnitude, which we'll call dA, and a direction n. So if I hold a piece of paper up to you, then yes, it's got a fixed amount of area, but how much of it you see depends on the normal vector. So if I align it so that the normal vector is vertical, you see very much less than if I align it like this. So an important quantity to bear in mind is that we'll have to think about area as a vector. This is going to be really important when we start to think about forces acting on surfaces, because we're going to have a little element of area of size dA. It's got a unit normal, n, as we've just described, and we're going to be thinking about forces acting on that area. And so since we're thinking about it on a per area basis, so there'll be a little area dA, then we're going to need to think about force per area. And the word in English that's often used for that is to think about this as a traction force or a traction vector, which has units of force per unit area. And what sometimes causes confusion is to recognize that there's another thing that has units of force per area, and that is that stress is also has units of force per area. And so we'll need to think about how to compare those two different ideas. They both have in SI units of pascals. This one, if I multiply it by the area, I'm going to get a force, so it's a vector quantity. This quantity, however, is not a vector quantity. And the way to think about this is that if I'm thinking about force, which is a vector, like as I've written here, and I'm dividing it by the area, dA, then I have to think about the idea that I have a force which is a vector and another quantity that's a vector. And those two may be aligned, they may be misaligned. And so in general, we have two free indices. And so we're going to typically represent this in terms of a second rank tensor. So this is called a second rank tensor, which has two free indices. So if I write it in component form, it'll have a component tau ij multiplied by two free indices ei and ej. So the tech symbol for this is tau. And it comes from the idea that we're thinking about a force, which is a vector, and dividing it by an area, which is also a vector. And so we'll be using this a lot as we think about these different forces. So there are three classes of forces that we're going to have to think about. First of all, body forces. These are quite easy to think about. Secondly, surface forces, which are a little bit more complicated because we have to understand this idea of a tensor quantity. And then finally, line forces. which, as you might imagine, have different dimensions, as we'll think about them in terms of how they scale with the size of an object, but they're all going to ultimately be forces. So the first one, the one that we're most familiar with, is a body force. And we've already seen some of those ideas, I'm sure, if you've taken an undergraduate class, where you might have thought about something that was simpler, like let's take our particular volume and make it just, say, a mug of water or a bottle of water like this. And so there's no flow out of the system, and we might be interested in thinking about what happens when it comes to rest. And we know that there's a body force acting on this, which is nothing but the weight of the object. So in general, in this class, we're only going to be thinking about what people would call a conservative body force, such as gravity. And a conservative body force means that we can represent the force in terms of the gradient of a potential. And the potential would be a scalar, and so typically we might write a gravitational body force per unit mass, so this is a force per unit mass, in terms of the gradient of some potential, which I'll generically represent by pi. Okay? And so this is again, a body force that we can think about. So this is a force per unit mass. And we'll think about the idea that then if I want to convert it into a total force, then I just multiply it by the mass of the system. And of course, if I'm interested in it on a small basis for a little material element, then the element of mass here is just going to be equal to rho dV. And so the force that we might say that's acting on a little element there would be G times rho times del V. Now here we're only going to think about a conservative body force, but in general, body forces, more generally, arise from action at a distance. So we've put this glass of water or something in a gravitational field, and we get this. But there are other forces that can also act on things which are not conservative. And so we just should bear in mind that there can be, in many cases, non-conservative body forces. The most common examples are electromagnetic body forces. And so those, when they arise from, say, placing a material like a conducting fluid in an electric field or in a magnetic field, lead to much more complicated forces. We're not going to think about them in this class. But if you were interested in this, the particular area of interest is what people would typically call Magneto Hydrodynamics. And people who are interested in the Earth's dynamo, or people who are interested in solar flares or in plasma fusion or developing fusion reactors are certainly interested in this area of what people would call magneto hydrodynamics. However, in the rest of this class, we're just going to think about conservative body forces. And so the key idea of this idea that we can write it in terms of a gradient of a potential is that this force is path independent. So the weight of this object that I might be weighing here is exactly the same no matter how I raise it through the potential field in the Earth. So I can get to this point and it weighs something. If I do a much more complicated path through a system, when I get here, the potential is still the same, the gradient of the potential is still the same, and it still weighs the same. So that's the kind of body force that we'll think about. In the next lecture, we're going to think about the next of these classes of forces, which is surface forces.